Okay, ionic solids. The ionic compounds have crystalline structures that are going to be related to the unit cells that we talked about, but because we have two kinds of ions, cations and anions, instead of just one, it gets a little more complicated. The coordination number here represents the number of close cation-anion interactions, which would lower the potential energy. In general, the more similar the size of the cation and anion, the higher the coordination number, because they're going to fit together better. We've got three things we have to balance for crystal structures of ionic compounds. We've got the coordination number. We have charge neutrality, because we're limited in the ratio of ions. Some of them are 3-to-1 or 2-to-1 or 1-to-1. And then we also have different ion sizes. So I am not going to expect you to be able to regurgitate any of this. I just want to give you an idea for some of the issues that you have to consider with these sorts of crystals. Yes? Charge neutrality and ion size. So first we're going to start by looking at ionic solids where the ions are similar in size. So here chloride and cesium are similar in size, so these can pack together better than if one of them is really big compared to the other one being really small. Now, when we look at this, what kind of a unit cell does that look like? It looks like body-centered, right? But in the body-centered, the one body in the middle was the same kind of element or atom as the ones in the corner. And here, the cesium is a different one, okay? So when we identify the cube or the unit cells here, we have to focus on just one kind of ion. So if we look at just the chlorines and ignore the cesium, what is this? Simple cubic, okay? In this simple cubic, we would have the equivalent of one chloride ion, and then we can see that there's that one cesium ion sitting in the middle. There have to be equal numbers because cesium's +1, chloride's -1. Something like calcium sulfide would have a similar structure. Again, the ions are similar in size, and it's a 1-to-1 ratio. You have a question? It's not a body-centered. So it's not body-centered because this is a different kind of ion.
So if it was body-centered, it'd all be cool.
Yeah, if this was green, it'd be body-centered. And then the cesiums would have to be stuck in between somewhere.
To be face-centered, would it?
Then you'd have to have green ones on the faces too. So what's a little, I think, confusing about this is when we first started talking about them, we were looking at purple and gold balls, right? And we had purple balls and a gold ball in the middle, and we called it body-centered. But I did say, and I tried to emphasize, we use the different colors there just so we can see it better. They're actually all the same. They're all identical. Here, this is not the same type of ball as this. So maybe these are limes, and that's a plum in the middle. And when we look at the unit cell, we have to just focus on one piece of fruit so that we can reproduce this. I don't have a special name written on the slide. I'm sure there is a name for it. This one has a name. This is the rock salt structure. So this one with purple and green, now this is harder to look at because with all the purple ones in there. Try to ignore the purple ones. Well, maybe I could do this. Make them kind of disappear. Now, looking at just The green ones, what kind of a unit cell is that? So here's the face. Here's one face of it, right? And we have a sphere at each corner. And what do we have in the middle? We have one on the face, centered on the face, and there's one centered on this face, and one centered on this face, face-centered. They're hard to look at. So this is face-centered with the sodium ions in between. If we didn't have to worry about charge neutrality, we could pack these in a lot closer together because the sodium ions are very small compared to the chlorine, and there's a lot of space in here. We could pack in more, but we can't do that because then the charge wouldn't be neutral. So we have to have an equal number of cations and anions.
So the other one was just a simple.
The first one was simple cubic, where the other ion was in the middle. Here we have body centered with the other ion in between. Now here's a question. In this unit cell, how many sodium ions and how many chloride ions? Well, let's just think about the green ones that are forming our slightly familiar shape of a face-centered cubic structure. How many atoms were in the face-centered? 4, right? We had half an atom on each of 6 faces, and then the corners all add up to 1. So there are 4 atoms. There must be 4 chloride ions in this structure. So what does that tell us about how many sodium ions there are? We could look at this by charge neutrality, or we could try to visualize what's going on there with the purple spheres. I choose charge neutrality. If there's 4 chloride ions, there must be 4 sodium ions. There's 1 in the middle, and this would be a quarter and a quarter and a quarter and a quarter, and you can add those all up, and that should give you 4. Well, the edges, let's see, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's 12 that there's a quarter of. So that's 3, plus the one in the middle. The coordination number here is only 6, is less than in the previous example. This is called a rock salt structure, and there are other compounds that take on this structure. Yes?
So what kind of packing?
This is not a closest packed. Not closest packed. Yeah, it's not closest packed. So that was a size difference between the cation and the anion. And then when we get an even bigger size difference, the coordination number is going to drop to 4. This is called the zinc blend structure. It's the structure that zinc sulfide takes on. And again, let's try to look at just the yellow spheres. And what kind of a thing do we have going on here? It's still face-centered, right? It's still face-centered. The difference between this one and the previous one, though, is where the other ion is. So in this one, we had the small ion in between along the edges, and here they're in the middle. They're in here. So if we look at 4 of these yellow spheres, they make a tetrahedron, and there's a hole in the middle, and so that's called a tetrahedral hole. There's actually 8 tetrahedral holes inside of that sphere, the unit cell, and there'll be zinc ions in 4 of them. If you have a 1-to-2 ratio, this is calcium fluoride. Hopefully we're getting a little more familiar with looking at this. I'll draw the box again now. So there's our corners, and there's this one in the middle. This is face-centered still. But now these lighter green ones are occupying all 8 of the tetrahedral holes that are present. So that's because we have a 1-to-2 cation to anion ratio. We have 2 fluorides for every calcium. So we have to have twice as many fluoride ions as we have calcium ions. The opposite of this is called the antifluoride structure, and that's where you have 2 cations for every 1 anion. So I'm not going to be asking you about these specific structures. I just want you to be aware of the complicating factors in what structure a crystal forms. It's more than just packing spheres in as close as possible. We have to have the right ratio, the charge neutrality, and then the relative sizes make an effect as well. We're not going to do that one.